Okay, so let's start off with this week's tutorial, right? The solution is already uploaded on your Moodle shell, right? You can see, I think, under week 3's, on your Moodle shell, just go under week 3 section and you can find homework 2 solution, I think, right? Anyways, you can find the solution on Moodle already uploaded, right? So this week's tutorial is quite lengthy actually. So let's just quickly start off with this, right? So the first problem is based on Shannon's capacity theorem, right? According to the Shannon's channel capacity theorem, channel capacity is equal to C is equal to B times log of base 2 of 1 plus S and R, right? Where C is the capacity, B is the bandwidth, S and R is signal to noise ratio. Okay. So, okay. So answer the following questions with respect to the channel capacity theorem. 1, when the bandwidth increases, what happens, right? So when the bandwidth increases, what will happen? The channel capacity will increase, right? Based on just observing this particular formula, you can see that if the bandwidth increases, the capacity also increases, right? 2, okay, let's directly go to the solution of 1 first, right? When the bandwidth increases, what happens? As the bandwidth increases, the channel increases, right? Or the channel capacity increases. It is possible to make faster changes in the information signal, thereby increasing the information rate and hence the channel capacity, right? So if the channel capacity increases, that means more information can be broadcasted, right? And it gives you much more, it gives a possibility of faster information transfer, right? 2, when the SNR to signal ratio, when the signal to noise ratio increases, what happens? So if the signal to noise ratio increases, one can increase the information rate while still preventing errors due to the noise, right? So signal to noise ratio, if signal to noise ratio increases, what that indicates is that we'll be having more signal compared to noise, isn't it? So if there's more signal compared to noise, if the SNR increases, what happens? The quality of the information is intact, right? So there is less room for errors in that, right? Or less distortion caused by the noise in the channel, right? 3, when the signal to noise ratio or the SNR tends to infinity, what happens? So if SNR goes to infinity, what will happen, right? If you go see this particular formula, it is a log of base 2, right? Isn't it? So it is basically a logarithmic part, right? So we are taking log of an SNR value, right? If you plot the log graph, it is basically going to increase, right? All of you know how a log graph looks like, right? Isn't it? So based on that, if the SNR increases to infinity, what happens is that that a infinite information rate is theoretically possible, right? Irrespective of the bandwidth of the channel. Okay. So 4, when the bandwidth tends to infinity, what happens, right? If the bandwidth increases to infinity, what will happen? If the bandwidth increases to infinity, the channel capacity does not approach infinity, since with an increasing bandwidth, the noise power also increases. Okay. So that's regarding the first question, right? Question number 1, right? So make sure you remember all this series, right? Okay. Question number 2, Shannon's and Nyquist equations. Suppose that the spectrum of a channel is between 10 megahertz and 12 megahertz, and an intended capacity of 8 megabits per second, right? So from this particular part or this particular statement over here, we can make out that the channel spectrum is between 10 megahertz and 12 megahertz. So basically the bandwidth is 2 megahertz, okay, based on this. And the intended capacity of the of the network is 8 megabits per second, right? Now, what should be what should be the SNR in order to obtain this capacity, right? So what happens is that we need to go back to pardon. Anyways, so the first thing, I mean, like, we just need to find what should be the SNR in order to obtain the capacity, right? So if you go back and look at the Shannon capacity formula, right, in this particular case, we know our bandwidth, right? We don't, we know our bandwidth. Do we know our capacity, right? We know our capacity, right? We know our bandwidth, we know our capacity. So we can compute our SNR value from this particular formula, isn't it? By making SNR the subject of the formula, we can compute or calculate the value of SNR, isn't it? So doing so, right, making SNR the subject of the formula in this particular case, right, these two should have been subscript. Remember, it's a small 2 that is indicating that this is a logarithmic of base 2, right? So in this particular case, we make SNR the subject of the formula. And once we have that, right, making SNR the subject of the formula, we can feed our capacity and bandwidth information into that, right? So making SNR the subject of the formula, this is what we get. That is 2 to the power of C divided by B, whole thing minus 1, okay? So substituting all these values, we get SNR is equal to 15, right? Is that fine? All of you can get that? You can punch this in your calculators right now. So far, is everything okay? Guys?
Yes, sir.
Okay. Okay, great. So I believe you can feed in the information, right? If you do this, 2 to the power of 8 megabits, right? So that would be 8 times 10 to the power of 6, right? Divide by bandwidth is 2 megahertz. So that is basically 2 times 10 to the power of 6 again. So that gives us 2 to the power of 8 divided by 2. So basically 2 to the power of 4, right? Whole thing minus 1. So if we do that, 2 to the power of 4 will give me 16. Minus 1 is going to give me SNR value of 15. Okay. How many signaling levels are required to obtain this capacity, right? This is where our Nyquist equation comes in, right? So Nyquist equation or Nyquist theorem basically states that the capacity is equal to 2 times B, right? 2 times the bandwidth times log of base 2 of M, where M is any number of order M is any value of base 2, right? So it can be M is equal to 2, M is equal to 4, M is equal to 16. 2, 4, 8, 16, right? You can see that there is a base of 2, isn't it? So 2 to the power of n, right? M is basically equal to 2 to the power of n, right? So any value of base 2, right? Okay. So based on this, we just need to calculate how many signal levels are required to obtain this capacity. So M is what is our signal levels, right? M is the number of signal levels, right? So making M the subject of the formula, will be left with 2 to the power of C divided by 2 times B, right? Which is going to be equal to M. So now from this particular case, we know our channel capacity, right? Channel capacity, which is 8 megabits per second, or 8 times 10 to the power of 6 bits per second, right? While our bandwidth is basically 2 megahertz, or 2 times 10 to the power of 6, right? So substituting the values, you should get M is equal to 4. Okay. Question number 3. So this, for question number 2, this is simple mathematics. I believe all of you should be able to do this, right? It's direct substitution. Please try to do this, right? Question number 3, what would be the capacity if the environment starts suffering lesser noise and the SNR goes up to 27 dB? So we want to know our capacity, right? Previously, we knew our capacity. Now we don't know our capacity, right? We know our SNR value, right? SNR value is in dB, right? And what else do we know? We know bandwidth. So we know bandwidth, we know SNR. Which formula do we use? Shannon's or Nyquist? So you can see Shannon's formula and the Nyquist theorem over here. Both the theorems are there. So which one do you use? The first one or the second one? So we use the first one, right? So we use this one, right? The Shannon's capacity theorem. This is where, I mean, this involves the SNR value, right? So we know our SNR value is 27 dB. So do we use this 27 dB, right? No, right? Because all our values are in standard units, right? We have to change this dB into normal signal to noise ratio formula. I mean, in normal unit formula, right? We have to change this dB into normal SNR value, right? So in order to compute the decibel value of any value, we use 10 times log of base 10 of some value, isn't it? So in this particular case, we are doing it for SNR, right? So as the value of SNR in dB is basically equal to 10 times log of base 10 of SNR, right? So what we do is make SNR the subject of the formula in order to compute the in order to convert the dB to normal standard units, right? So we know that the dB is 27 decibels, so we convert this 27 decibels into standard unit, and we'll be getting SNR is equal to 501, right? 501. That is the approximate value, right? Moving on to, I mean, now we know SNR value, right? The standard SNR value, right? So we know standard SNR value, we know bandwidth, right? We need to compute our capacity, right? So what we do is take our SNR value and the bandwidth value, whatever we have over here, we substitute it in the Shannon's theorem, right? Shannon's theorem is this, right? This over here. So in this particular formula, we substitute our bandwidth value and we substitute our SNR value, right? So that will be basically C is equal to 2 times 10 to the power of 6, right? In place of B, it will be 2 times 10 to the power of 6 times log of base 2 of 1 plus the SNR value is 501, right? And evaluating that, we'll get our capacity, which is equal to 18 megabits per second. Okay. So moving on to question number 4. Question number 4 is same question as 2, but for capacity in 3. So what did we get? The capacity in 3 is basically 18 megahertz, right? 18 megahertz. So in this particular case, what happens is we have our, so we have to use this capacity value, right? So capacity is basically 18 megahertz, and we have to do it for same question as in 2. So question number 2 is how many signaling levels are required to obtain this capacity? So we know our capacity, we know our bandwidth, we just need to calculate our M. Okay. So again, using this same formula, right, that we got, M is basically equal to 2 to the power of C divided by 2B. In that same formula, we directly substitute our C value, right, the capacity over here, which we got in question number 3. Part number 3, sorry. We take this capacity value and our bandwidth value that we have, right, that is constant, right? We take this and this particular value and substitute it in the formula, and we should get M is equal to 2.6, right? Okay. So what happens is that, like I said, M is, just hold on. Let me just quickly evaluate this. So that will be 2 to the power of C. So C is 18 megahertz divided by 2B. So 2B is 4. So am I getting, yeah, I'm getting M is equal to 2.6, 22.6, right? So now the number of channels will be in decimals or integer value. What do you think? Can the number of channels be in fraction? William, what do you think? No, right? So what happens is that we have to approximate this, right? So this is basically approximately equal to 23, right? Okay. Now, like I said, this m value has to be of order 2, right? 2 to the power of n values, right? This m has to be of this particular value, right? M is basically equal to 2 to the power of n, right? N can be any integer value, right? Based on this, 2 to the, if we set m is equal to 23, that would not suffice this particular condition over here. M cannot, so m is basically, we cannot find any n value to which our 2 to the power of n value is going to give us 23, right? So we have to see the nearest value. So in that particular case, m, if we do m is equal to 2 to the power of 2 to the power of 5, we should get 2 to the power of 5, we are going to get 32. And if we do 2 to the power of 4, right, one digit less, we are going to get 16. So if 16 is, let's just quickly write all the values of 2 to the power of n. So the first one is when n is equal to 1, it's going to be 2. When n is equal to 2, it's going to be 4. Next would be 8, right? Next is 16. And next is 32, right? So when n is equal to 1, we have 2. N is equal to 2, we have 4. N is equal to 3, we have 8. N is equal to 4, we have 16. And when we have n is equal to 5, we have 32. Now, based on this, towards which does 23 lean towards? 32 or 16, right? So based on that, right, we have to make our decision. What will be the value of m? Okay. Remember, m has to be of this particular order over here. M has to be some value of 2 to the power f of n, right? So it has to be close to these values, right? So in this particular case, 23 is basically closer to 32. Okay. So that is why m is equal to 32, which is more realistic solution, right? So remember, if you're giving the value of m, it has to be of this particular order. M is basically equal to 2 to the power of n, where n is basically equal to any integer value. Okay. So we got 23, right? We got 22.6. So number of channels cannot be in decimals. It has to be in integer values, right? Number of channels, right? It has to be in integer value. So that is why we round it off. We get 23. And then we know that m cannot be any value, right? It has to be of base of 2, right? It has to be a value of base 2, right? So based on that, we find the nearest value of m, which is going to give us 32. Okay. Moving into the next question, right? Anyways, moving into the next question. Okay. So we have finished with question number 2. So anyone has any question regarding question number 2? So all of you will be able to solve this?
Yes, sir.
Yes. Okay. Yes, Thomas. What's? Oh, okay. You mean you can solve this, right? Okay, it's basic substitution, right? You should be getting the same solution. Okay. Okay. Let's move on to the next part, right? Question number 3 or problem number 3. What do you mean by dynamic equalization, and what problems does it tackle? 2 is, why is it that when you increase the data rate of a communication system, typically the error rate increases? Part 3 is, explain the forward error correction scheme with an applicable example. 4 is, what are the advantages and disadvantages of the spread spectrum techniques? 5 is, give an example that proves the channel reciprocity does not apply to wireless links, right? Question number 1, what do you mean by dynamic equalization and what problem does it tackle? So the solution states dynamic equalization is a method in which multiple delayed copies of the same signal are combined at the receiver. It is usually a weighted process in which the delayed copies of the signal are assigned weights dynamically before combining them. This method tries to offset the effects caused due to multipath, which cause intersymbol interference by trying to reconstruct the original signal by using multiple copies received, right? So what this is basically trying to tell us, dynamic equalization is basically, you have a sine wave, right? You have a sine wave. When you are transmitting sine wave, if you are transmitting any particular wave, right, you can reconstruct that same signal using a particular signal which is basically delayed, or what do you say, its amplitudes are varied, right? So let me just quickly show you an example, maybe, right? Let me just go and search it up on Google. Dynamic equalization, right? So that you can understand what I mean, right? Okay, you can see this particular signal right over here. Okay, not that one. Let's find a much clearer signal for you guys to understand. Okay, let's just take this particular signal over here, right? We can construct the main audio signal over here, this particular signal over here, using one particular type of signal to construct this dynamic signal, right? So what that indicates, let's say this is our main signal, right? This is our original signal. So in this particular case, what we do is we transmit a sine wave, right? We transmit the sine wave, and that particular sine wave will have you can have multiple copies of that same particular sine wave, right? And you can delay that particular sine waves, right? That those, like, let's say we have 10 particular sine waves. That 10 particular sine waves can fluctuate in its phases, right? So let's say first one goes, and after 10 seconds, there's second sine wave goes, right? So by doing that, each particular sine wave is varying by some particular phase, isn't it? Or is being delayed by some particular value, right? And each particular sine wave will have its own weight, right? But when we mean by weight, what that means is, let's say the first sine wave that we transmit at, let's say, t is equal to 0 second, right? What happens is that that particular sine wave might have a amplitude of 1, right? And then the second sine wave that is being transmitted at t is equal to, let's say, 2 seconds, right? After a 2-second delay, that particular sine wave can have an amplitude of 2, right? Likewise, the combination of all these, right? The combination of all these sine waves, and right, can construct, right, a given signal, right? So that is what is basically indicated by this, right? So dynamic equalization is a method in which multiple delayed copies of the same signal, right? Like I said, multiple copies of the same signal are combined at the receiver, right? So you have a particular signal, right? So multiple copies of that particular signal will be transmitted at different amplitudes and different phases, right? So I mean, by phase, what I mean is that they are being delayed at different times, right? So those signals are being transmitted having different amplitudes and different time frames, right? It is usually a weighted process in which the delayed signals of this signal are assigned weights dynamically before combining them. So like I said, weight is basically over here translating to the amplitudes, right? This method tries to offset the effects caused due to multipath, which cause intersymbol interference. So basically, when we mean by multipath, right, the term itself says that, tells you what multipath is, right? So you reach a particular route through multiple paths, right? So what this happens is, this tries to offset the interference that will be caused by or caused through each and individual path, right? So at the receiver end, these copies of the signal come together to form the original signal back, right? Or give you the original signal back, trying to reconstruct the signal, right? Okay. It's not necessarily, I mean, over here, when we are meaning by dynamic equalization, we are not trying to take another signal or try to bring in another copy of the signal. It is the same signal being transmitted at different delays, or that particular signals having different delays, right? And having different weightings, right? To offset the interference caused by the noises in their particular parts, right? Okay. So all of you are okay with dynamic equalization? Do you understand what dynamic equalization is, right? Do you? Let me just quickly show you what is multipath. What do you mean by multipath? Let's say just, okay, multipath. Okay, this is what I mean by multipath, right? I think William has taken this course last year, so he understands what I actually mean, right? So this is what multipath is, right? Let's say we have a particular transmitting unit, right? And this is our receiving unit, right? So we have a modem and we have a phone, right? This is our transmitting unit, this is our receiving unit, right? So the multipath philosophy or the multipath theorem is basically what it says is that there could be multiple ways or multiple paths of signal being received by the phone itself, right? The signals will radiate this way, this way, this way. It can radiate into multiple paths. So, but in this particular diagram, it shows 3 particular paths over here, right? So in dynamic equalization, what happens is this same signal is being transmitted in different directions, isn't it? Or in different paths at different delays, at different time delays, right? Okay, at different time delays, and these particular signals will have different weightings, right? So this is due to the interference caused by these buildings, right? These are all obstacles, right? If this signal bounces off this particular wall, right, it will lose some energy, and there could be some external interference caused by this particular building, or some sort of distortion caused by this building, or any equipment in between, right? So it can cause some sort of distortion in between, right? So once the distortion is caused, right, let's say there is a distortion caused somewhere over here, right, in this particular path. So this particular path has no distortion, right? Let's say this particular point is somewhere here in this particular path, right? So what happens is, if there is a defect over here in this particular signal, I mean this particular point in this particular path, there is no what do you say? There is no distortion in the signal over here, right? At the same particular point in this particular path. So what happens is, now once the receiver receives it, it can determine whether the signal has been distorted or not, right? So it is able to reconstruct the same signal, avoiding the interference caused by this multipath that has been taken by the object, right? Okay. So that's regarding dynamic equalization, right? Moving on to question number 2, part 2. Why is it that when you increase the data rate of the communication system, typically the error rate increases? So suppose that the presence of a given noise pattern corrupts n bits, right? When you increase the data rate and looking at the time domain, the space between the bits is shorter. So if the same noise pattern and everything else fixed, we double the rate, then at least 2 times n bits would be corrupted, right? So what this particular line over here actually means is that this means is that let's say we have a particular fixed point, right? So let's say we have this particular point over here, right? And then we have a set of information, this signal passing through, right? At the moment, at the moment, let's say, as the signal passes through this particular point, right? Let's say at the moment it takes the signal from this particular point to reach this particular point over here, or this particular area is sorry, let me list this, is 10 milliseconds, right? 10 milliseconds. Okay, now what happens is we know that there will be an interference caused in this particular signal, right? Let's say 5 milliseconds over here. Okay, example, I'm saying there is interference caused at 5 milliseconds as it passes through this particular point, right? Okay, now when you increase the number of rate, what happens is that this particular signal starts to go at a faster rate, right? So if you increase the rate, what happens is the time taken to reach this particular point will decrease, isn't it? It will decrease. Okay, I guess everyone can understand that, right? So what happens is if you increase, let's say, if we double this the rate of this particular signal, the time taken from the signal from this particular point to this particular point will decrease. It will decrease to 5 milliseconds, and the error occurring will be now at 2.5 milliseconds, right? So in the same space of time now, in the same 10 millisecond space of time, we'll be having two sets of errors occurring, right? Because this same set of three pulses will be doubled. If you increase the rate at which the signal passes this particular point, that means there will be two sets of this same signal being passed through this particular point, isn't it? That means each set having one set of error, right? At 5 milliseconds. So what happens is in this particular case, if you increase the rate of the data speed, right? At a particular, let's say if you double the rate, the speed of the, if you double the rate of the signal transmission, right? The error rate will also increase, okay? So this is what this statement basically says, right? So suppose there is the presence of a noise pattern corrupts n bits, right? When we increase the data rate and looking at the time domain, the space between each bits is shorter, right? So what it means is when you increase this, I mean, like I said, at the moment, if it's taking 10 milliseconds to pass this, it will take less time now, right? When we increase the speed of the data rate, so it will take around 5 milliseconds to pass the same number of pulses through this particular point, isn't it? So in that particular case, what happens is the time between each pulses, like each set of pulses, like at the moment it is 10 milliseconds apart from the next set of 3 pulses, right? So in the next set, I mean, when you increase the data rate, the time between each pulse will decrease, right? Okay, basically the time between each pulses will decrease. So if with the same noise pattern and everything else fixed, right? Every parameter is fixed, we double the rate of the data rate. So what happens is the number of bits getting corrupted becomes, or number of errors in that particular set of signal also increases, right? Okay. So in this, when we are transmitting signal, it is in digital form, right? So it is in n bits, not in pulses. So I just showed you something in analog form, right? But it will be the number of bits that will be corrupted, right? Okay. So all of you get that particular bit? Are you okay with that now? Okay. Are you guys okay with this? Or do you need some other explanation?
Yes, okay.
Okay, right? Okay.